Have you ever heard the universe whisper its secrets? Right now, drifting through the endless black, there are sounds, real, recorded sounds, that defy explanation. One of them, captured by a deep space probe, echoes like a ghostly moan, a low-frequency hum with no known source. Scientists call it the space roar, and it's just one of countless cosmic riddles waiting to be unraveled. The more we explore, the more the universe reveals its strangeness, objects that shouldn't exist, signals with no origin, forces that bend the very rules of physics. And today, we're diving into 30 of the most mind-bending discoveries that have left even the brightest astronomers scratching their heads. Picture a star that flickers like a faulty light bulb, dimming and brightening in ways no star should. Or a galaxy spinning so fast it ought to tear itself apart, yet somehow it doesn't. These aren't scenes from science fiction. They're real, documented phenomena, each one a puzzle piece in a cosmos that's far weirder than we ever imagined. Some of these oddities hint at entirely new laws of nature, while others point to forces or objects we can't even name yet. And the most thrilling part: every new telescope, every mission, every breakthrough adds another layer to the mystery, proving that we've barely scratched the surface of what's out there. This journey isn't just about cataloging cosmic curiosities, it's about stepping to the edge of human understanding and peering into the unknown. Each of these 30 oddities challenges what we think we know, inviting us to question, to wonder, to reimagine the universe itself. Some will unsettle you, others might make you gasp, and a few, well, they might just keep you up at night staring at the sky with fresh eyes, so buckle up. We're about to venture into the deepest, darkest, and most dazzling corners of space, where the ordinary ends and the extraordinary begins. Let's begin. Out in the vast expanse of space where darkness usually reigns, a newly discovered nebula pulses with an eerie, almost otherworldly glow. Astronomers have nicknamed it the Space Jellyfish for its long, flowing tendrils of gas that ripple outward like something alive. But this isn't just a beautiful cosmic accident, it's a cosmic anomaly that shouldn't exist according to our current understanding of how nebulae form. Located nearly 5,000 light-years away, this glowing structure defies the typical life cycle of stellar nurseries. Most nebulae are sculpted by the violent winds of newborn stars or the explosive deaths of old ones, but the space jellyfish's delicate filaments seem untouched by such forces. Instead, they stretch across light years in perfectly symmetrical waves, as if some unseen hand had carefully arranged them. What makes this nebula truly bizarre is its light. Unlike most nebulae, which glow from the heat of nearby stars, the space jellyfish emits an unnatural blue hue, one that doesn't match any known chemical process in space. Some researchers suggest it could be the result of an entirely new type of energy transfer, perhaps even dark matter interactions. Others theorize its structure might be a cosmic fossil, the remnants of a star that died in a way we've never witnessed before. The more we study it, the clearer it becomes. This isn't just a nebula. It's a clue, a whisper from the universe that our textbooks might be missing whole chapters on how space works. And then there's the strangest detail of all: those tendrils aren't drifting aimlessly. They're pulsing. Observations show faint but rhythmic shifts in brightness, almost like a heartbeat with no detectable source. No known stellar object nearby could cause such precise, repeating patterns. It's as if the nebula itself is alive, breathing in the void. That rhythmic flicker has sparked wild but serious debates among astronomers. Could this be evidence of some exotic physics we haven't discovered yet? A sign of cosmic-scale magnetic fields weaving through space, or something even more unexpected? The space jellyfish doesn't just challenge our models, it dares us to rethink what's possible. And with every new observation, this celestial mystery only deepens, reminding us that out there, beyond the edge of our understanding, the universe still holds wonders we can't even name. There's a cosmic predator lurking in the constellation Sagittarius, and it's not a black hole or a rogue star. It's a pulsar with a taste for destruction. Meet the Black Widow, a spinning stellar corpse so relentless that it's slowly evaporating its own companion star into oblivion. Pulsars are already some of the most extreme objects in the universe, ultra-dense neutron stars that beam radiation like lighthouses as they rotate at mind-blowing speeds. But the Black Widow takes this ferocity to another level, spinning nearly 700 times every single second. That's so fast, its surface moves at roughly a quarter the speed of light, flinging charged particles into space with enough energy to outshine entire galaxies in gamma rays. What makes this pulsar truly sinister, though, is what it's doing to its neighbor. Locked in a death spiral just 2 million miles apart, closer than Mercury orbits the Sun, the companion star is being blasted by a constant storm of radiation and particle winds. Over time, this relentless assault has stripped away nearly 90% of the star's mass, leaving behind a scorched, shrunken husk. Astronomers call this process Black Widow evaporation, and it's as brutal as it sounds. The pulsar's gravity pulls material from its partner, but instead of peacefully accreting it, the Black Widow shreds the stolen gas with its magnetic fields, converting it into deadly gamma-ray jets. It's a one-sided cosmic war, and the pulsar is winning. But here's the twist: the companion star isn't going down without a fight. Observations reveal it's not just a passive victim. It's fighting back with its own magnetic field, creating bizarre, pulsing distortions in the Black Widow's emissions. This tug-of-war has produced some of the most energetic gamma-ray bursts ever recorded, flashes so intense they briefly outshine the pulsar itself. Scientists are still unraveling how such a small, withering star can muster this defiance, but one theory suggests its core might be unusually dense, a last-ditch fortress against annihilation. The Black Widow Pulsar isn't just a celestial oddity, it's a laboratory for physics pushed to the brink. Its extreme environment challenges our understanding of how matter behaves under crushing gravity and unimaginable magnetic forces. And while its nickname might sound like science fiction, the reality is even stranger. This is nature at its most unforgiving, a reminder that even in the quiet of space, there are predators lying in wait. Deep in the cosmos, an object floats that looks like it was plucked straight from a cartoon, a perfect, glowing question mark suspended in the void. Astronomers first spotted this bizarre formation while studying a pair of young stars, and at first, many assumed it was some kind of imaging glitch. But multiple telescopes confirmed it was real, a cosmic structure shaped so precisely like the punctuation mark that it seems almost intentional. Located roughly 1,000 light-years away, this celestial question mark stretches nearly 5 times wider than our solar system, its curved hook and round dot glowing with the warm light of ionized gas. So what could create such an eerily symbolic shape? The leading theory suggests we're witnessing the aftermath of a violent galactic collision. When two galaxies merge, their gravitational forces can stretch and twist stars and gas into wild, unpredictable formations like cosmic taffy pulled into strange new shapes. In this case, astronomers speculate that two smaller galaxies might have sideswiped each other, their tidal forces sculpting this perfect punctuation in the chaos. But here's where it gets even stranger. The question mark appears to be floating alone, with no obvious remnants of the galaxies that supposedly created it. Did they drift apart after their encounter, leaving only this ghostly symbol behind? Or is something else entirely at play? Others argue it could be a rare line-of-sight illusion, a chance alignment of unrelated structures that, from our vantage point, just happen to resemble a question mark. After all, pareidolia, the human tendency to see familiar shapes in randomness, is why we spot faces in clouds or animals in constellations. But the crispness of this formation makes that explanation feel unsatisfying. Unlike fuzzy cloud-like nebulas, the edges of this structure are sharply defined, as if etched into space itself. What's truly fascinating is how this cosmic oddity has captured imaginations far beyond the astronomy community. It's gone viral, sparking jokes about the universe, asking us a riddle or demanding we rethink our place in it. Scientists, too, have leaned into the metaphor, calling it the universe's way of reminding us how much we still don't understand. And maybe that's the point. Whether it's a collision fossil, an illusion, or something even stranger, this glowing question mark hanging in the dark serves as a humbling reminder. For all our knowledge, the cosmos still has plenty of mysteries left to unravel. Every time we think we've got space figured out, it throws us a curveball, or in this case, a giant glowing symbol of curiosity. Stretching across the cosmic canvas like invisible ink, suddenly revealed, enormous rings of radio waves drift between galaxies, so vast they could swallow our Milky Way whole without a trace. Astronomers call them odd radio circles, or ORCs, and they're among the most baffling structures ever detected in space. Discovered just a few years ago by the Square Kilometre Array telescope, these ghostly halos span up to 2 million light-years across, dwarfing entire galaxies, yet emitting nothing but faint radio whispers. They don't correspond to any visible objects, no stars, no dust, no known sources of energy. It's as if the universe dipped a giant's finger in radio waves and pressed it against the dark. So what could create such colossal, invisible rings? One leading theory suggests they might be the aftermath of a cataclysm beyond comprehension, intergalactic shockwaves from supermassive black holes merging in the early universe. When two of these monsters collide, they release energy equivalent to billions of supernovae, potentially sending ripples through the intergalactic medium that persist for eons. Imagine throwing a stone into a pond. Only the pond is the fabric of space itself, and the ripples never fade. But there's a problem. These circles are too perfect. Shockwaves tend to be messy, chaotic things, while ORCs are eerily symmetrical, their edges crisp as if drawn with a cosmic compass, another possibility. Wormholes, or rather, the fossils of them. Some theorists propose these circles could be the mouths of ancient wormholes that collapsed long ago, their immense gravitational echoes frozen in radio waves. It's a wild idea, but the math holds. A collapsing wormhole might leave behind a ring-like disturbance in spacetime's background energy. Of course, that raises even more questions. If these are wormhole gravestones, where did the tunnels lead, and what, or who might have traveled through them? Then there's the strangest clue of all. ORCs seem to prefer hanging around galaxies like ours, almost as if they're drawn to them. Some appear perfectly centered on their host galaxies, while others orbit at a respectful distance. This cosmic etiquette has scientists wondering if these circles are somehow feeding on galaxies, siphoning off energy in ways we can't yet detect. Radio telescopes have caught faint hints of polarization within the rings, suggesting powerful magnetic fields at work, fields that could be twisting space itself. For now, ORCs remain cosmic Rorschach tests, revealing more about our curiosity than their true nature. Every new observation peels back another layer of mystery. Are they echoes of forgotten violence, artifacts of alien engineering, or something we haven't even dreamed up yet? One thing's certain. In a universe full of surprises, these silent, sprawling rings remind us that some of its greatest secrets don't glow, don't blaze. They hum quietly in the dark, waiting to be heard. Hidden in the constellation Ursa Major, a cosmic feast is underway, one that's been raging for billions of years. The so-called cannibal galaxy, officially known as Messier 82, isn't just growing, it's consuming its neighbors in a slow, violent ballet of gravity and destruction. This isn't some abstract astronomical concept. We're watching it happen in real time, with telescopes capturing streams of stars being torn from smaller galaxies and dragged into the cannibals, glowing more like celestial spaghetti. What makes this galaxy so voracious? Size and opportunity. Messier 82 is a classic example of a brightest cluster galaxy, an oversized behemoth that anchors the center of its galactic group. Over time, its immense gravity has drawn in smaller galaxies, stripping them apart in a process called tidal disruption. The evidence is etched across the cosmos. Ribbons of stars, stellar streams, stretch for hundreds of thousands of light years, marking the paths of galaxies that ventured too close. Some streams are still fresh, their stars loosely bound and glowing with the heat of recent trauma. Others are ancient, their structures frayed into faint smudges barely visible against the black. But here's the twist: this galactic cannibalism isn't just about destruction. It's a creative force. Every devoured galaxy adds new stars, gas, and even dark matter to Messier 82, reshaping its structure in unpredictable ways. Some of the stolen stars end up in chaotic orbits, buzzing around the cannibal's core like angry bees. Others settle into its outer halo, building a vast, diffuse shell of stellar refugees. This constant influx of material might explain why Messier 82 is so unusually bright. It's been gorging itself on cosmic scraps for eons, growing fatter as its neighbors grow fewer. The most breathtaking detail: we're seeing this play out in a way that suggests our own Milky Way could one day suffer the same fate. Just as Messier 82 dominates its group, the Andromeda Galaxy looms as the titan of our local neighborhood. In about 4 billion years, when Andromeda and the Milky Way collide, our galaxy could become the next meal in this universal food chain. Stellar streams already encircle our own galaxy. Ghosts of smaller systems it's absorbed in the past, proof that even the Milky Way isn't above a little cosmic cannibalism. Yet for all its violence, there's a strange beauty in this process. The cannibal galaxy isn't some mindless predator. It's a sculptor molding the cosmos through collision and assimilation. Its feuds forge new star clusters, redistribute precious metals, and even trigger bursts of star formation. In devouring its neighbors, it's not just destroying, it's recycling, seeding the next generation of celestial objects. And that's the unsettling lesson of Messier 82. In the grand timeline of the universe, even galaxies aren't permanent. They merge, they warp, they consume and are consumed. The cannibal galaxy isn't an aberration, it's a preview of how all galaxies, ours included, might one day meet their end. In the cosmic badlands of deep space, there's a neutron star behaving so wildly, so unpredictably, that astronomers have dubbed it the Tasmanian Devil. This isn't your average dense stellar corpse. It's a luminous fast burster, a rare breed of neutron star that occasionally erupts with energy so intense it outshines entire galaxies for mere milliseconds. But what sets this particular object apart isn't just its power, it's the sheer ferocity and frequency of its outbursts. In one unprecedented event, it unleashed over 80 explosions in just 4 months, some spaced less than an hour apart. That's like a cosmic machine gun firing bursts of energy powerful enough to vaporize planets, all from an object no bigger than a city. The Tasmanian Devil's tantrums defy everything we thought we knew about magnetar's neutron stars with ultra-strong magnetic fields. Typically, magnetar flares are thought to occur when their crusts crack under intense magnetic stress, releasing pent-up energy like a coiled spring snapping. But this celestial troublemaker doesn't play by those rules. Its bursts are shorter, sharper, and far more frequent than any magnetar should theoretically produce. Even stranger, the energy released doesn't match the slow build-up and sudden release model instead. It's as if the star has a hidden reservoir of power, tapping into it at will. Some scientists speculate it might be feeding off an unseen companion, siphoning material that triggers chain reactions deep in its core. Others wonder if we're witnessing an entirely new type of stellar behavior, one where magnetic fields reconfigure themselves in milliseconds, like cosmic lightning rearranging itself mid-strike. Then there's the mystery of its light. Unlike typical magnetar flares, which glow brightest in X-rays, the Tasmanian Devil's outbursts peak in visible light. A glaring, white-hot flash so intense it briefly outshines its entire host galaxy. That shouldn't happen. Neutron stars are supposed to be too cold on their surfaces to produce such brilliant visible light. The leading theory: these bursts might be heating surrounding debris to unimaginable temperatures, turning stray particles into temporary light bulbs floating in the star's deadly magnetic web. As for its nickname, it wasn't just chosen at random. Like the cartoon whirlwind it's named after, this neutron star leaves scientists just as bewildered as Bugs Bunny dodging its chaos. Every time researchers think they've figured out its pattern, it throws another curveball, erupting when least expected or going silent for months before roaring back to life. Some have even joked that if the universe has a sense of humor, this star is its punchline, a cosmic reminder that no matter how many rules we write for how stars should behave, there's always an exception waiting in the dark. And that's what makes the Tasmanian Devil so thrilling. It's not just an oddity, it's a challenge, a dare from the cosmos to rethink what's possible when matter is pushed to the absolute limit. Right now, an invisible storm is barreling through our galaxy at 500,000 kilometers per hour, a hurricane of dark matter so vast it could rewrite our understanding of the universe's hidden architecture. Astronomers call it the S1 stream, but its nickname, the dark matter hurricane, captures its terrifying grandeur. Unlike earthly storms, you can't see this one coming. It leaves no visible trail, no swirling clouds, just a violent ripple in the motions of stars, the only clue that something massive, something utterly unseen, is tearing through space. This cosmic tempest began its journey billions of years ago when a smaller galaxy ventured too close to the Milky Way. Gravity shredded the intruder, stretching its stars into a long, looping river, a stellar stream that still orbits our galaxy today. But here's the eerie part: the visible stars are just the tip of the iceberg. The real weight, the real menace, comes from what we can't see. Calculations show the stream's gravity is 10 times stronger than its visible stars can account for. That missing mass, it's dark matter, the universe's most elusive substance, moving through us right now like a ghostly gale. The hurricane's speed is what makes it so extraordinary: 500 kilometers every second, fast enough to cross the United States in less time than it takes to blink. If you stood in its path, not that you'd feel a thing. Trillions of dark matter particles would pass through your body every second, their gravity subtly tugging at your atoms. Normally, dark matter's signals are drowned out by cosmic noise, but this storm offers a rare opportunity. Its dense, concentrated flow might finally let us detect dark matter directly. Experiments like XENON and LUZ are on high alert, their underground detectors waiting for the faintest shudder, a particle collision that could prove dark matter isn't just theoretical. Yet the hurricane holds another mystery: its shape. Stellar streams usually follow predictable orbits, but this one twists like a writhing snake, its path warped by unseen forces. Some researchers suspect the Milky Way's dark matter halo. An enormous, invisible cloud surrounding our galaxy is denser than we thought, its gravity bending the stream into these bizarre contortions. Others propose an even wilder idea: that the hurricane might be grazing another invisible structure, a clump of dark matter drifting like a phantom island in the galactic sea. The most thrilling possibility: this storm could be our first real look at dark matter's fine structure. Most models assume it's smoothly distributed, but if the hurricane's distortions come from smaller clumps, it would mean dark matter isn't just a featureless fog. It has texture, substructure, perhaps even its own hidden geography. Every star caught in this stream is a breadcrumb leading us deeper into the unknown, a trail of clues left by a force that makes up 85% of the universe's mass yet refuses to be seen. The dark matter hurricane isn't just passing through. It's forcing us to confront how little we truly understand about the invisible scaffolding of reality itself. In the quiet depths of the cosmos, two dead stars performed a dance so subtle, so strange, that it defied every expectation of how stellar lives should end. Astronomers stumbled upon the aftermath, a lone white dwarf glowing with an unnatural pale hue, its atmosphere made almost entirely of helium, a composition that should have been impossible. This wasn't just any remnant of a dying star. It was a cosmic ghost story, the remains of two white dwarfs that merged in perfect silence, skipping the spectacular supernova explosion that should have marked their violent union. White dwarfs are typically the cooling embers of stars like our Sun, dense Earth-sized cores left behind after a star sheds its outer layers. When two of them collide, the result is usually a Type 1, a supernova, one of the brightest explosions in the universe. But this pair, catalogued as WD0825+353, broke the rules. Instead of detonating, they fused together like celestial phantoms, leaving behind a single, bloated white dwarf with a surface temperature colder than it should be and an atmosphere stripped of the usual heavier elements. It's as though the stars vanished into the night without a sound, leaving only this eerie, helium-rich relic behind. The mystery lies in how they pulled it off. Merging white dwarfs are supposed to reach a critical mass threshold around 1.4 times the mass of our Sun, triggering a runaway thermonuclear explosion. But this zombie star clocks in at just under that limit, suggesting one of two bizarre scenarios. Either the stars were lightweight enough to merge gently, like two droplets of ink blending in water, or they did briefly cross the threshold and somehow stabilized afterward, a cosmic Houdini act that shouldn't be possible. The latter idea has theorists scrambling. Could some white dwarfs survive their own doom by rapidly spinning or ejecting mass at the last second? Or is there an unknown mechanism that presses pause on supernova, allowing dead stars to resurrect themselves in this ghostly form? Then there's the helium enigma. Most white dwarfs have atmospheres dominated by hydrogen or heavier elements like carbon and oxygen, the ashes of nuclear fusion. But this one's helium blanket suggests something stripped away its outer layers long ago, leaving only the star's intermediate shell exposed. One provocative theory. The merger might have triggered a hidden furnace deep inside the star, reigniting nuclear burning just long enough to consume its hydrogen veneer before flickering out again. That would make this object a kind of stellar Lazarus, briefly clawing its way back from death before settling into its current spectral state. Perhaps the most unsettling thought is what this means for the cosmos. If silent mergers like this are common, astronomers might be missing entire populations of failed supernova events that should have lit up the sky but instead slipped away unnoticed. It's a humbling reminder that even the most catastrophic stellar events can sometimes whisper rather than scream, and that's the haunting beauty of this ghostly white dwarf. It challenges not just what we know about stars, but how we listen to the universe itself. Some stories aren't told in flashes of light or shockwaves of energy. Some are written in the quiet, in the elements left behind, in the gaps where explosions should have been. Somewhere in the Milky Way, an outlaw is on the run, a black hole unlike any other, traveling solo through the galaxy's outskirts with no star to call its own. This isn't a supermassive monster anchoring a galaxy's heart or a binary predator locked in a gravitational tango. It's a lone wanderer, invisible yet undeniable, detected only by the way it bends the very fabric of space around it like a cosmic funhouse mirror. Astronomers first caught its trail not by light or radiation, but by accident, a single star in the constellation Sagittarius suddenly brightening for no apparent reason. But this wasn't a flare or a supernova. As telescopes zoomed in, they realized the star's light was being stretched and magnified, warped by an unseen object passing in front of it. The culprit, a black hole roughly 7 times the mass of our Sun, drifting silently through interstellar space, and that's what makes it so impossible. Stellar mass black holes aren't supposed to exist in isolation. They're born from the explosive deaths of massive stars, and those stars almost always have companions. Even after a supernova, the black hole should remain gravitationally bound to its partner, feeding on it or at least orbiting it for billions of years. This one, though, is utterly alone. No neighboring star, no accretion disk, no trace of its past. It's as if it was ejected from its birthplace with unimaginable force, hurled into the void like a bullet fired into the dark. The leading theory suggests a violent origin story, a three-star system where chaos reigned. If two of the stars collapsed into black holes and merged, the resulting kick from gravitational waves could have sent the newborn black hole careening outward, abandoning its third sibling entirely. The math checks out. The energy from such a merger could launch a black hole at speeds over 1,000,000 miles per hour, fast enough to escape even the tightest stellar bonds. But here's the catch: we've never caught one in the act until now. What's even stranger is how quiet this black hole is. Without gas to feed on or a companion to strip material from, it emits no X-rays, no radio waves, nothing but the subtlest distortion of starlight. That makes it nearly invisible to traditional detection methods. In fact, astronomers estimate there could be hundreds of millions of these rogue black holes lurking in our galaxy, ghosts slipping between the stars, their presence known only by the way they occasionally twist the light of distant suns. And that raises a chilling question: how many have already passed through our solar neighborhood undetected? A close encounter with one of these wanderers wouldn't rip planets apart. Its gravitational pull would be too localized, but it could subtly alter orbits, flinging comets from the Oort cloud inward in a deadly shower. Some researchers even speculate that past mass extinctions on Earth might bear the fingerprints of a rogue black hole's distant passage. For now, this lone outlaw remains a tantalizing enigma, a reminder that even the darkest, most isolated corners of the galaxy hold secrets waiting to be unraveled. Every time we think we've mapped the universe's extremes, it throws another curveball. This time, a shadow without a home, drifting silently through the night. Imagine a planet so light and fluffy, you could theoretically scoop it up with a spoon, if, of course, you had a spoon roughly the size of Earth. Meet TOI 3757b, the cosmic equivalent of a marshmallow floating in the void. This Jupiter-sized world shouldn't exist according to our current models of planetary formation. It's not just big, it's bloated, with a density lower than any gas giant we've ever found. To put it in perspective, if you could plunge Saturn into a cosmic swimming pool, it would bob like a beach ball. But TOI 3757b, it would practically float away like foam on the surface. So how does a planet grow this light? The answer might lie in its star, a temperamental red dwarf prone to violent tantrums. Most gas giants form far from their host stars, where icy building blocks are plentiful, then migrate inward over time. But TOI 3757b orbits so close, a single year lasts just 3.5 Earth days, baking under relentless stellar radiation. Normally, this heat would cause a planet's atmosphere to puff up, but not to this extreme. The secret might be the star's unpredictable flares. Red dwarfs are notorious for erupting without warning, bombarding nearby planets with enough X-rays and ultraviolet light to strip atmospheres entirely. Yet somehow, this planet's thick gaseous envelope remains intact. Here's where it gets counterintuitive. Those same flares might be the key to its fluffiness. Scientists suspect the intense radiation could be heating the planet's core less efficiently than expected, preventing its interior from compacting under gravity. Think of it like baking a soufflé: too much heat too fast and it collapses, but gentle, uneven heating might leave it airy and unstable. There's also the possibility of exotic chemistry at play. The planet's atmosphere might be rich in water vapor or methane, molecules that absorb stellar radiation differently than the hydrogen-dominated air of typical gas giants, creating a buffer against atmospheric loss. But the real shocker, TOI 3757b, might not be alone. Recent surveys suggest marshmallow planets could be surprisingly common around red dwarfs, a whole class of worlds defying our expectations. If that's true, it would mean our understanding of planetary evolution has a glaring blind spot. We've spent decades assuming gas giants follow predictable blueprints, but this cosmic confectionery proves otherwise. Sometimes the universe doesn't just break the rules, it rewrites them entirely, leaving us staring at the sky with a mix of wonder and confusion. And that's the delicious irony of this discovery. The squishiest planet we've ever found might be the one that finally forces us to rethink how all planets grow. Somewhere beyond the edge of everything we can see, something massive is pulling. An invisible hand yanking entire galaxy clusters toward it at impossible speeds. Astronomers call this phenomenon the dark flow, and it's one of the most unsettling cosmic mysteries of our time. Imagine throwing a handful of leaves into a river, only to watch them all drift stubbornly upstream against the current. That's essentially what's happening here, except instead of leaves, it's thousands of galaxy clusters, each millions of light years wide, all being dragged toward a single point in space like moths to some unseen flame. The dark flow was discovered by accident while studying the cosmic microwave background, the afterglow of the Big Bang. Scientists noticed something bizarre. Clusters of galaxies weren't moving randomly as expected. Instead, they showed a coordinated drift toward the constellation Centaurus at speeds exceeding 2 million miles per hour. That's faster than any known force in the universe should allow. Gravity from visible matter can't explain it. Dark energy, the mysterious force accelerating cosmic expansion, should be pushing everything apart, not pulling it together. So what could possibly be strong enough to tug entire clusters like toys on a string? One chilling possibility: the dark flow might be evidence of structures outside our observable universe, cosmic giants so enormous, their gravitational influence spills over into our pocket of reality. Picture standing in a valley, feeling a wind you can't see because its source lies beyond the mountains. That's what we might be experiencing here. Some theorists suggest these could be unimaginably vast concentrations of mass, perhaps other universes brushing against ours in the multiverse, or remnants of a pre-Big Bang reality we can't yet comprehend. Nicknamed the Space Kraken for its unseen, all-reaching influence, this force hints at a cosmos far larger and stranger than we ever imagined, but not everyone's convinced. Skeptics argue the dark flow could be an illusion, a statistical fluke or measurement error amplified by the sheer scale involved. Others propose more exotic physics, like quirks in spacetime itself, that create preferential directions for motion. The truth is, we lack the tools to see beyond the cosmic horizon, that ultimate boundary where light from the early universe hasn't had time to reach us in 13.8 billion years. Whatever's out there remains hidden, its presence inferred only by the way it tugs at the edges of our reality. Here's what makes this enigma so thrilling. If the dark flow is real, it means our universe isn't just lopsided, it's connected to something beyond. The implications rewrite cosmology. Maybe the Big Bang wasn't the true beginning. Maybe what we call the universe is just a bubble in a vaster cosmic ocean, one where currents flow between shores we can't yet see. Every new observation deepens the mystery, leaving us with more questions than answers. And that's the heart of science, isn't it? The moment we think we've mapped the edges of existence, the universe whispers no, yanks us toward the next great unknown. Deep in the heart of our galaxy, a celestial rebel is rewriting the rules of stellar behavior, one erratic flicker at a time. Magnetar SGR 1935 plus 2154 isn't just another dense neutron star with a powerhouse magnetic field. It's a cosmic glitch, a stellar malfunction that suddenly sped up, slowed down, and unleashed some of the most powerful radio blasts ever recorded, behavior so bizarre it might finally solve one of astronomy's greatest puzzles, the origin of fast radio bursts. Most magnetars are predictable in their unpredictability. They crack under magnetic stress, releasing bursts of X-rays and gamma rays in fits and starts. But SGR 1935 plus 2154 breaks the mold. In 2020, it did something unprecedented. It stuttered. Over the span of just 3.7 seconds, the magnetar's rotation slowed dramatically, as if something inside it had jammed. Then, mere hours later, it spat out a millisecond radio burst so intense it was detectable across the galaxy. That flash wasn't just loud, it was a landmark. For the first time, a magnetar's tantrum matched the signature of a fast radio burst, those mysterious cosmic screams that have baffled scientists for over a decade. But the real shock came months later when the star began speeding up. Normally, neutron stars gradually slow as they age, their spin sapped by magnetic drag. This one did the opposite, revving up like a cosmic engine hitting the gas. The leading theory, a starquaker, a sudden rearrangement of the magnetar's crust under unimaginable pressure. Picture Earth's tectonic plates shifting, only scaled up to stellar extremes. Crustal plates the density of atomic nuclei snapping and rebounding, releasing enough energy to alter the star's spin in an instant. When this happens, the star's superfluid interior neutrons flowing without friction might slosh against the crust, transferring angular momentum in violent fits and starts. It's like stirring a cup of coffee with a spoon, then watching the liquid suddenly spin the spoon on its own. Here's where things get truly extraordinary. Those speed changes might be the key to the magnetar's radio outbursts. As the star's rotation stutters, its already insane magnetic field, a quadrillion times stronger than Earth's, gets twisted into knots. When these magnetic tensions snap, they could launch blasts of charged particles at near light speed, generating shock waves that emit coherent radio waves. That would explain why this magnetar's radio bursts resemble fast radio bursts. They might share the same engine. And if that's true, it could mean that at least some of those enigmatic intergalactic signals aren't coming from alien megastructures or colliding black holes, but from misbehaving stellar corpses in our own cosmic backyard. Yet mysteries remain. Why do some glitches produce radio flares while others don't? How can a star's interior transfer energy so efficiently? And most perplexing of all, why is this magnetar so loud compared to others? Its 2020 burst was 1,000 times more energetic than any previous magnetar radio emission, blurring the line between typical magnetar activity and the far more powerful fast radio bursts from distant galaxies. Some scientists speculate that SGR 1935 plus 2154 might be a transitional object, bridging two classes of phenomena we once thought were unrelated. Every flicker, every speed change, every radio scream from this magnetar is a clue, not just about neutron stars, but about the fabric of reality itself. The forces at play here push matter beyond any conditions we can replicate on Earth, into realms where protons and electrons behave in ways that defy textbooks. And that's what makes this glitching star so thrilling. It's not just an oddity, it's a Rosetta Stone, helping us decode some of the universe's most energetic and elusive signals. With every erratic pulse, it whispers a challenge. Listen closely, the cosmos has more to say. Jupiter's great red spot isn't the only atmospheric behemoth stirring up chaos on the gas giant. Lurking in its northern latitudes, a second, even more enigmatic storm churns. A colossal dark vortex so cold, it defies everything we know about planetary weather systems. Nicknamed the Great Cold Spot, this sprawling tempest stretches 24,000 kilometers across, wide enough to swallow Earth twice over, yet it's invisible to the naked eye. Unlike the iconic red spot, which burns crimson with rising heat, this anomaly is a frigid void, a patch of atmosphere hundreds of degrees colder than its surroundings, held together by forces we're only beginning to understand. What makes the Great Cold Spot so baffling isn't just its size or temperature, it's its persistence. Most atmospheric features on Jupiter are fleeting, lasting days or weeks before being swallowed by the planet's violent jet streams. But this icy monstrosity has endured for decades, possibly centuries, reappearing in observations like a ghost in the clouds. The red spot owes its longevity to Jupiter's east-west winds, which keep it spinning like a cosmic top. The cold spot, though it shouldn't exist, it sits in a region where atmospheric currents should tear it apart, yet somehow it clings to stability like a boulder in a hurricane. The leading theory suggests this isn't a storm at all, but the aftermath of something far more exotic, auroras on a scale unimaginable on Earth. Jupiter's magnetic field is a monster, 20,000 times stronger than ours, and when solar particles collide with its poles, they don't just create pretty lights. They unleash enough energy to send shockwaves rippling through the atmosphere, potentially carving out this permanent cold pocket thousands of kilometers away. Think of it like a cosmic freezer door left ajar, with auroral winds funneling frigid gas downward while surrounding currents trap it in place. But here's the twist. Recent data reveals the spot isn't just cold, it pulses. Observations show its temperature and shape fluctuate wildly, sometimes vanishing entirely before reforming months later. That's left scientists wondering if it's not one single structure, but a series of transient vortices constantly being reborn, like bubbles rising in a pot of boiling water. Some even speculate it could be a window into Jupiter's mysterious interior, a sign of heat welling up from deep below only to freeze solid in the upper atmosphere's brutal chill. The Great Cold Spot does more than just puzzle astronomers. It challenges our definitions of what a weather system can be. On Earth, storms are born from temperature gradients and moisture. On Jupiter, they might be sculpted by magnetic chaos and particles screaming down from space. And that's the humbling truth this icy enigma drives home. The universe doesn't just scale up familiar phenomena. It reinvents them entirely, crafting wonders that force us to rethink the very laws we thought governed the skies. In the silent void of space, a comet once sang, not with words or music, but with the haunting hum of magnetic waves. Comet 67P, known as Churyumov-Gerasimenko, became famous not just for its rubber duck shape, but for the eerie melody picked up by the European Space Agency's Rosetta probe. As the spacecraft drew closer in 2014, its instruments detected something unexpected: oscillations in the comet's magnetic field, pulsing at 40 to 50 millihertz, far below human hearing, but when sped up 10,000 times, they revealed an uncanny, almost ghostly song. This wasn't just random noise. The singing came from interactions between the comet's nucleus and the solar wind, a stream of charged particles racing from the sun. As these particles bombarded 67P, they energized gases boiling off its surface, turning the comet's surrounding plasma into a vibrating membrane. Imagine blowing across the top of a bottle, but instead of air, it's the fabric of space itself resonating. What made this chorus so unusual was its stability. Most comets produce chaotic bursts of radio waves, but 67P's oscillations were remarkably steady, almost like a tuning fork struck in the vacuum of space. The song held secrets about the comet's hidden structure. By analyzing the frequencies, scientists realized 67P's nucleus was far more porous than expected, with cavities and tunnels allowing solar wind to penetrate deep beneath its surface. This spongy interior acted like a cosmic flute, channeling and amplifying the vibrations in ways a solid body couldn't. Even more intriguing, the melody changed as the comet neared the sun, its pitch shifting with the intensity of outgassing, a proof that its composition was dynamic, evolving in real time as sunlight peeled away layers of ancient ice. Yet the biggest surprise was what the singing didn't explain. For decades, researchers assumed comets were surrounded by dense magnetic bubbles, created when ionized gas from their tails trapped solar wind. But Rosetta found almost no evidence of such a bubble around 67P. Instead, the magnetic field lines appeared to dance through the comet, weaving around it like invisible threads. That discovery appended models of how comets interact with their environment, suggesting their magnetic influence might be far subtler and far stranger than we thought. Then, as suddenly as it began, the song faded. When 67P reached its closest approach to the Sun, the increasing outgassing disrupted the delicate plasma vibrations, silencing the chorus. But in those fleeting months, this singing comet gave us something rare, a direct, audible connection to an ancient wanderer. Its melody wasn't just a curiosity, it was a language translating the invisible forces shaping these icy time capsules. And perhaps that's the most humbling lesson of all. The universe doesn't just show us its wonders. Sometimes, if we listen closely enough, it sings them to us. Far beyond our solar system, a planet endures a storm more extravagant than any fairy tale, a perpetual downpour of diamonds. WASP 121b, a searing hot Jupiter orbiting perilously close to its star, hosts conditions so extreme they transform carbon into glittering crystalline showers. This isn't poetic speculation, it's hard physics. With temperatures soaring above 2,500 degrees Celsius on its day side and crushing atmospheric pressures over 100 times greater than Earth's, this exoplanet is a factory for the universe's most coveted gemstones. The recipe for diamond rain begins with methane, a molecule rich in carbon. Under normal circumstances, methane drifts harmlessly through gas giants like Jupiter. But on WASP 121b, the dayside heat tears these molecules apart, liberating carbon atoms. Violent winds moving at nearly 5 kilometers per second sweep the carbon to the cooler night side, where mind-bending pressure squeezes the atoms into diamond structures. Imagine clouds of soot crystallizing midair, then falling as gemstone hailstones into the planet's molten depths. Laboratory experiments on Earth have recreated similar conditions, proving the process isn't just theoretical, it's a tangible, if alien, form of weather. Yet the true marvel lies in what happens next. These diamonds don't linger near the surface. As they sink deeper, pressures escalate to over 1 million times Earth sea level, transforming the gems into something even stranger, liquid carbon. This molten diamond sea might slosh around the planet's core, churned by convective currents until rising heat vaporizes it back into the atmosphere, completing a cycle as surreal as it is beautiful. It's a cosmic alchemy that turns starlight into treasure, only to melt it down and start anew. The irony, for all its extravagance, WASP 121b is utterly inhospitable. Its diamond showers aren't nestled in some fantasy cavern, they're trapped in a hellish maelstrom of supersonic winds and eternal twilight. The planet's orbit is so tight that tidal forces have stretched it into a football shape, locking one face permanently toward its star while the other languishes in frigid darkness. This extreme contrast drives the very storms that craft its jewels, a reminder that nature's most dazzling spectacles often arise from brutality. What's most humbling is the scale. While Earth's water cycle moves droplets, WASP 121b's diamond cycle likely shuffles tons of carbon in a perpetual, glittering avalanche. Some models suggest larger diamonds could form, perhaps even iceberg-sized clusters, though we'll never mine them. The planet's gravity is so intense, any spacecraft daring to descend would be crushed long before glimpsing its crystalline wonders. This exoplanet does more than dazzle, it redefines our understanding of planetary chemistry. Who knew the same element in pencil lead could, under the right torment, become a sky full of diamonds? It's a lesson written in starlight and pressure. The universe doesn't just create life or landscapes. Sometimes it crafts jewelry on a planetary scale, then hurls it into the abyss. Most planets follow the cosmic rulebook. They orbit their stars in the same direction the star spins, like runners circling a track in orderly lanes. But out in the constellation Hercules, a rebel world flips the script entirely. TOI 2180b isn't just any gas giant. It's a planet that moves backwards, hurtling around its star in a direction so opposite, it defies everything we thought we knew about how planetary systems form. This cosmic maverick was discovered by NASA TESS telescope, which caught its silhouette as it transited across its star's face. At first glance, it seemed ordinary, a Jupiter-sized world with a year lasting 260 Earth days. But when astronomers mapped its orbit, the shock set in. TOI 2180b's path is tilted a staggering 178 degrees relative to its star's rotation. In other words, it's not just retrograde, it's perfectly misaligned, as if someone hit rewind on its motion while the rest of the system played forward. How does a planet end up so spectacularly out of step? The answer might lie in gravitational chaos. Most planets form from swirling disks of gas and dust that inherit their star's rotation, aligning their orbits like grooves in a vinyl record. But TOI 2180b likely didn't stay put. One theory suggests it was born farther out, then got yanked inward by interactions with another massive object, perhaps a second gas giant or a passing star. These gravitational shoves could have sent it careening off course, flipping its orbit like a flipped pancake midair. Here's where tidal forces enter the equation. As the planet spiraled closer, its host star's gravity would have pulled harder on one side than the other, stretching and kneading its interior like cosmic taffy. Over billions of years, that relentless tug of war could have sapped its orbital momentum, leaving it stranded in this bizarre backwards dance. It's a slow-motion celestial wrestling match where the star ultimately wins, but the planet refuses to go quietly. What's truly baffling is that TOI 2180b shouldn't have survived this ordeal. Hot Jupiter's gas giants hugging their stars usually have tight, circular orbits sculpted by tidal forces. But this one bucks the trend, maintaining an eccentric, elongated path despite its proximity. That defiance hints at a recent disruption, as if the planet's dance of defiance isn't over yet. Some researchers wonder if it's still settling into its rebellious ways, its orbit not quite frozen in place. This backwards world isn't just an oddity, it's a challenge to planetary formation models. If rogue interactions can fling giants into such extreme orbits, how many other systems hide similar rebels, and what does that mean for our search for Earth-like worlds? After all, a gas giant gone rogue could easily destabilize smaller, habitable planets, ejecting them into the void. TOI 2180b serves as a cosmic cautionary tale. The universe doesn't always play by the rules. Sometimes it rewrites them mid-game, leaving us to piece together the clues. High above the galactic plane, an elderly star has crafted its own funeral shroud, not in the usual messy clouds of gas, but with near-mathematical precision. The red rectangle nebula glows like a geometric ghost in the constellation Monoceros, its crisp lines and vivid crimson hue making it one of the most visually striking structures in the cosmos. At first glance, it looks less like a natural formation and more like an art installation, a colossal, cosmic window frame suspended in the void. This celestial masterpiece owes its shape to an extraordinary cosmic coincidence. Most planetary nebulae, the glowing shells ejected by dying stars, are chaotic and asymmetrical, bubbling outward like smoke rings. But the red rectangle's central star, HD 44179, is locked in a gravitational waltz with a companion, their orbital dance sculpting the outflowing gas into precise conical jets. Picture twin fire hoses spraying paint in opposite directions while spinning like tops. Over millennia, that spiraling motion has woven the nebula's distinctive lattice of rungs and crossbeams. The result, a near-perfect X-shape glowing with the light of ionized hydrogen, its edges so sharp they seem drawn with a ruler. What truly sets this nebula apart, though, is its color. The deep red hue comes from an exotic form of carbon-rich molecules called polycyclic aromatic hydrocarbons, essentially soot forged in the star's death throes. These compounds fluoresce under ultraviolet light, transforming the nebula into a sprawling cosmic neon sign. But the real spectacle lies in the finer details. Hubble's close-up images reveal intricate ladder-like rungs stretching between the X's arms, a structure so delicate it resembles stained glass lit from within. Astronomers suspect these rungs are shock waves, dense ripples where faster-moving gas rams into slower material, creating standing waves frozen in time. The strangest twist, this nebula shouldn't glow so brightly. The central star isn't hot enough to ionize the surrounding gas the way typical planetary nebulae do. Instead, the red rectangle's light may come from an unseen source, perhaps a disk of material around the companion star, glowing as it absorbs energy from the primary. Some even speculate the nebula's eerie symmetry hints at hidden magnetic fields, channeling the outflow like invisible wires guiding a marionette. While most stellar deaths are messy affairs, the red rectangle is a rare example of cosmic order emerging from chaos. Its perfection won't last forever. The central star will eventually cool, and those razor-sharp lines will blur into the interstellar medium. But for now, this dying star's final act is a reminder that even in the vast, turbulent universe, beauty can emerge in the most unexpected forms. And perhaps that's the nebula's real mystery, not how it formed, but why something so fleeting chose to leave behind a monument so precise, so deliberate, as if it wanted to be remembered. Most supernovae blaze brilliantly for weeks before fading into obscurity, but not SN2022JLI. This stellar explosion refused to follow the script, flickering like a malfunctioning light bulb with a rhythm so precise it left astronomers stunned. Instead of dimming steadily after its initial cataclysm, this cosmic detonation brightened and faded every 12.4 days like clockwork, a heartbeat of light echoing from a dead star. The culprit, a hidden companion that somehow survived the blast and is now locked in a macabre dance with the remnant, siphoning material back into the firestorm it helped create. This isn't just a surviving star, it's a cosmic vampire. When SN2022JLI's progenitor star exhausted its fuel and collapsed, the explosion should have annihilated anything nearby. Yet here, the companion endured, orbiting so close that it now plucks gas directly from the supernova's fading aftermath. Each time this star swings through the densest part of the debris cloud, it gorges on stellar material, triggering fresh bursts of energy. Think of it like a moth circling a flame, only this moth is stealing embers and fanning them back to life every 12th orbit. The resulting pulses are so regular, they've turned a chaotic stellar death into something resembling a cosmic metronome. What makes this system stranger still is the physics at play. Normally, supernova shocks blow companion stars away, yet this one held firm, its gravity anchoring it amid the chaos. Scientists suspect it might be a stripped-down helium star, its outer layers peeled away long before the explosion, making it compact and dense enough to weather the storm. Now, as it orbits the supernova's core, likely a neutron star or black hole, it's trapped in a feedback loop of destruction and rebirth. Material stolen from the explosion forms an accretion disk around the compact remnant, heating up and reigniting the fading light show with every pass. The implications stretch far beyond this one oddity. If surviving companions are more common than we thought, they could explain other mysterious supernova behaviors, like why some leave behind zombie stars or why certain explosions seem oddly lopsided. SN2022JLI might be the missing link, a Rosetta Stone showing how binary stars can twist stellar deaths into new, unexpected forms. It's a reminder that even in destruction, the universe finds ways to surprise us, turning a star's final act into an encore no one saw coming. Stretching across the void between galaxies like invisible bridges, vast cosmic filaments weave the universe into a single, interconnected web. These tendrils of dark matter and gas, some spanning hundreds of millions of light-years, form what astronomers now call the intergalactic superhighway, a hidden infrastructure guiding the motion of galaxies and shaping the large-scale structure of the cosmos. Recent 3D maps from projects like the Sloan Digital Sky Survey have revealed these filaments in stunning detail, showing how they act as gravitational conveyor belts, funneling galaxies toward dense clusters and superclusters with eerie precision. What makes these filaments so extraordinary isn't just their size, it's their role as cosmic architects. Imagine the universe as a bustling city. Galaxies are the buildings, clusters are the downtown hubs, and these dark matter threads are the subway lines connecting everything. They don't just sit idly, they actively channel matter, directing the flow of gas that fuels star formation and even dictating the orbits of entire galaxies. Simulations suggest up to 60% of all galaxies may be linked by these filaments, riding their gravitational currents like commuters on a rush-hour train. The most mind-bending realization, this superhighway might be the key to intergalactic travel, not for us yet, but for galaxies themselves. Take the Milky Way. We're hurtling toward the Great Attractor, a mysterious gravitational anomaly in the Virgo cluster at over 600 kilometers per second. That motion isn't random, it's guided by the pull of dark matter filaments, invisible hands steering us along a preordained path. Some astronomers compare it to a cosmic version of lane assist, where galaxies are subtly corrected to stay on course by the surrounding filament's gravity. Yet the filaments themselves are nearly undetectable. Dark matter doesn't emit light, so we only infer its presence by the way it bends space and tugs on visible matter. Gas trapped in these filaments does glow faintly, but it's so diffuse that spotting it requires stacking observations from thousands of pathways, like turning up the contrast on a photo to reveal hidden ink. The resulting images show faint, wispy strands of ionized hydrogen weaving between galaxies, ghostly reminders of the universe's underlying skeleton. What's truly humbling is how this superhighway underscores our cosmic insignificance. The filament connecting the Milky Way to Andromeda, it's part of a larger structure called the Laniakea supercluster, a gravitational watershed encompassing 100,000 galaxies. Even at our scale, entire galaxies are just waypoints along these vast, ancient roads laid down in the universe's infancy, when slight density fluctuations in the primordial soup set the stage for everything that followed. And here's the twist, these filaments aren't static. They evolve over billions of years, stretching as the universe expands, sometimes snapping under their own tension or merging like interstate exchanges. Some may even act as cosmic pipelines, funneling gas into galactic centers to feed supermassive black holes, a process that could explain why some galaxies suddenly flare to life as quasars. Others might host rogue, intergalactic stars, cast adrift from their home galaxies but still bound to the filament's gravitational flow. The intergalactic superhighway doesn't just connect the universe, it built it. Without these filaments, galaxies would be isolated islands drifting apart in the dark. Instead, they're nodes in a grand network bound by threads of unseen matter. Every time we map another section, we're not just charting space, we're reading the blueprint of existence itself, one invisible road at a time. Some stars die with a bang, others refuse to die at all. T Ursae Minoris, a crimson-hued variable star in the constellation of the Little Bear, has been cheating death for nearly a century, erupting violently again and again like a cosmic phoenix stuck on repeat. This isn't just a star that burns bright. It's a celestial zombie, a stellar anomaly that defies one of astronomy's most fundamental rules. When stars run out of fuel, they don't get second chances. Discovered over 100 years ago, T Ursae Minoris first seemed like a typical Mera variable, a pulsing red giant nearing the end of its life. These stars normally swell and shrink in predictable cycles, brightening and dimming as they burn through their remaining fuel. But in 1979, astronomers witnessed something unprecedented. Instead of fading gently into oblivion, T Ursae Minoris erupted in a violent thermal pulse, suddenly blazing thousands of times brighter than normal. That alone was strange, but what came next was downright eerie. Over the next 40 years, it erupted 4 more times, each outburst defying models of stellar evolution that say such events should be once-in-a-lifetime cataclysms. Time-lapse observations reveal a star in open rebellion against its fate. During eruptions, its surface bubbles like boiling water, ejecting massive shells of gas into space at speeds exceeding 30 kilometers per second. Yet instead of collapsing afterward, it somehow restabilizes, pulling material back in or tapping hidden reserves to keep burning. The latest eruption in 2020 even left behind a glowing halo of expelled material, a ghostly echo visible for months like smoke lingering after a firework. The leading theory, T Ursae Minoris, might be a rare, recurrent nova progenitor, a star locked in a toxic relationship with a white dwarf companion. As the red giant sheds material, the dense white dwarf could be hoarding it until critical mass triggers periodic thermonuclear explosions on its surface. But here's the twist: the intervals between eruptions don't match typical nova cycles. Instead of decades, they've ranged from years to just months, suggesting an instability deeper within the star itself, perhaps pockets of unburned helium igniting sporadically like time bombs in its core. What's truly unsettling is how this zombie star mirrors our own sun's future. In 5 billion years, our star will swell into a red giant too. Will it also sputter and flare unpredictably? Could it defy the quiet demise we've always assumed awaits it? T Ursae Minoris doesn't just challenge textbooks, it forces us to question whether we've underestimated stars' ability to fight back against the dark. Every pulse, every eruption is a message. Even in death, the cosmos resists simplicity. Some stars don't fade gently, they rage, they flicker, and sometimes, against all odds, they refuse to go silently. Hubble recently caught something unprecedented: a supermassive black hole fleeing its own galaxy at breakneck speed, dragging a comet-like trail of newborn stars behind it. This cosmic fugitive, weighing as much as 20 million suns, isn't just wandering, it's sprinting, clocking in at over 5 million miles per hour, fast enough to cross the distance between Earth and the Moon in under 3 minutes. And the most astonishing detail: the wake it leaves behind isn't destruction, it's creation. A river of blue hot young stars glowing defiantly in the void marks the path of this rogue titan like breadcrumbs from a fairy tale. So how does a black hole, an object so gravitationally dominant that light can't escape it, get evicted from its own galactic throne? The leading theory points to an ancient cosmic collision. When two galaxies merge, their central black holes eventually spiral together, locking into a gravitational dance that ends in a violent merger. Under just the right conditions, the energy released in that final union isn't symmetrical. Like a rifle's recoil, the blast can kick the newly formed black hole clean out of the galaxy. Simulations have predicted this gravitational recoil for years, but Hubble's discovery offers the first direct evidence: a black hole caught in the act of being thrown into the abyss. The real marvel, though, is that star-forming wake. As the black hole plows through intergalactic gas, its colossal speed compresses the material in front of it, triggering shock waves that ignite star formation in its path. Imagine a cosmic plow carving furrows into space, with stars blooming in its wake like wildflowers after a storm. These aren't just any stars, they're young, massive, and blazingly bright, their blue hue betraying their youth. Normally, such pristine stellar nurseries are found deep within galaxies, nurtured by dense gas clouds. Out here in the barren intergalactic medium, their existence defies all expectations. Yet the mystery deepens when you examine the trail's structure. It's not a straight line, but a wobbling, meandering path, suggesting the black hole isn't just sailing smoothly, it's stumbling, as if still reeling from the force that ejected it. Some astronomers speculate this could mean the black hole didn't get a clean kick. Instead, it might have been a messy, multi-stage ejection, perhaps involving a third black hole that complicated the merger dynamics. Others wonder if the black hole is dragging along remnants of its disrupted accretion disk, a swirling maelstrom of gas that could be fueling intermittent bursts of star formation like a dying engine sputtering to life. What's truly humbling is the scale of this runaway's journey. The star trail stretches an astounding 200,000 light-years. twice the diameter of our Milky Way, a testament to how long this exile has lasted. By now, the black hole has traveled so far from its birthplace that it may never return, doomed to wander the cosmic hinterlands forever. And that raises a chilling question: how many other supermassive black holes are out there, drifting unseen in the dark? Current estimates suggest up to 100 might be roaming our local universe alone, ghostly monarchs dethroned by ancient violence. This discovery does more than add another oddity to the list. It reshapes our understanding of black hole ecology. We used to think of them as stationary anchors, unmovable giants bound to their galaxy's hearts. Now we know they can be flung into the void, becoming nomads that reshape the cosmos as they go. And perhaps that's the most poetic twist of all. A force known for devouring light has become, against all odds, a reluctant midwife to new suns. The universe seldom obeys our expectations. Sometimes it hands us a paradox, a destroyer that creates, a fugitive that leaves beauty in its wake. One of the most dramatic cosmic performances in recent memory didn't come from a supernova or colliding galaxies. It came from a single, aging star in Orion's shoulder. Betelgeuse, the red supergiant that glows like a campfire ember in the winter sky, shocked astronomers in late 2019 when it began fading rapidly, dimming to just 36% of its usual brilliance by early 2020. This wasn't some gradual decline, it was a stellar freefall, as if the universe had turned a dial on one of its brightest landmarks. For months, the astronomy world held its breath. Was this the prelude to a supernova, a once-in-a-millennium event visible even in daylight, or was something even stranger unfolding? The answer turned out to be both less apocalyptic and far more fascinating. High-resolution images captured by the Very Large Telescope in Chile revealed the culprit, a colossal dust cloud belched from Betelgeuse's surface like a cosmic sneeze. Red supergiants are notoriously messy eaters, convulsing as they burn through their final fuel. In Betelgeuse's case, a massive bubble of hot gas likely surged upward from its churning depths, reaching the cooler outer layers where it condensed into solid particles, trillions of microscopic dust grains that temporarily veiled the star's light. Think of it like a smudge on a lighthouse lens, dimming the beam without extinguishing the flame. What made this event groundbreaking wasn't just the spectacle, it was the intimate look inside a dying star's tantrums. Betelgeuse's dimming provided the first direct evidence of how these volatile giants shed material before their eventual explosions. The dust cloud itself was staggering in scale. If placed in our solar system, it would have stretched from the Sun to beyond Mars. But the real surprise was the speed. Conventional models assumed dust formation happened gradually over centuries. Betelgeuse proved it could occur in months, rewriting our understanding of how quickly massive stars can reshape their own destinies. Yet the great dimming left behind as many questions as answers. Why did the dust form so asymmetrically, casting only a partial shadow? Could magnetic fields, usually an afterthought in red supergiant studies, have played a role in directing the outflow? And most tantalizingly, was this a routine burp or a sign of deeper instability? Some theorists now suspect Betelgeuse might be a post-merger star, its outer layers still settling after cannibalizing a smaller companion long ago. If true, its recent theatrics could be the stellar equivalent of indigestion, a bloated giant still processing an ancient cosmic meal, the most humbling lesson. We nearly missed it. Betelgeuse has likely staged similar dimming acts for millennia, but only with modern telescopes could we catch one in progress. It's a reminder that even the most familiar stars can harbor secrets, their quiet rhythms punctuated by moments of chaos. And while the show's over for now, Betelgeuse has since rebrightened. Its next act is inevitable. Whether in 10 years or 10,000, this star will explode. When it does, the great dimming will be remembered as its dress rehearsal, a fleeting glimpse of the turbulence brewing beneath that crimson glow. For now, we watch, we learn, and we wait knowing that in the grand theater of the cosmos, even the oldest players can still deliver surprises. Most planets orbit a single star, basking in its steady light, but one world has taken cosmic multitasking to the extreme. Circling the triple star system GW Orionis, this exoplanet lives a life of perpetual celestial drama, with not one, not two, but 3 suns painting its skies. If that sounds like something out of Star Wars, you're not wrong. Astronomers nicknamed it the Tatooine planet, though Luke Skywalker's home only had to deal with twin suns. This real-world oddity doesn't just defy sci-fi, it upends our very understanding of how planets form in chaotic stellar environments. What makes this system so extraordinary isn't just the planet's triple sunrise, it's the warped, pretzel-shaped disk of dust and gas that birthed it. Normally, protoplanetary disks are flat, orderly structures like vinyl records spinning around young stars, but GW Orionis's disk is anything but tidy. 3 gravitational masters, 2 stars locked in a tight binary orbit, and a third whirling farther out have yanked and twisted the disk into a labyrinth of misaligned rings, some tilted as much as 38 degrees. It's as if a child grabbed the edges of a frisbee and bent it into a crumpled hat. This cosmic tug-of-war has sculpted gaps and kinks where planets could coalesce, creating nurseries in places theorists once thought impossible. The real shock came when astronomers spotted a planet nestled within this gravitational chaos. Conventional wisdom said planets couldn't form in such unstable environments. Competing stellar gravities should shred protoplanetary material before it can clump together. Yet there it was, a gas giant roughly the size of Jupiter, orbiting its primary star at a distance that would place it between Mercury and Venus in our solar system. How did it survive the stellar trio's gravitational bullying? The answer might lie in the disk's twisted geometry. Those warped rings could act as protective cocoons, shielding growing planets from the worst of the turbulence. Alternatively, the planet might have formed farther out and migrated inward, riding waves of disturbed gas like a surfer on a cosmic tide. But the most mesmerizing detail isn't the planet, it's the light show overhead. Depending on its orbit, this world might experience alternating cycles of single, double, or triple sunrises with shadows stretching in 3 directions at once. For stretches of its year, 2 stars could dance close together in the sky while the third hangs distantly, a faint but constant companion. Other times, all 3 might rise and set in hypnotic succession, casting ever-shifting hues across alien clouds. The seasons, if they exist, would be a chaotic mess with gravitational nudges from each star potentially yanking the planet's axis back and forth over millennia. This system doesn't just challenge textbooks, it forces us to rethink the limits of planetary resilience. If worlds can form in such extreme environments, what other cosmic rulebooks need rewriting? Could there be planets orbiting quadruple or even quintuple star systems? And what does that mean for the search for habitable worlds? After all, if a planet can survive the gravitational roller coaster of GW Orionis, maybe life, against all odds, could too. The universe keeps reminding us when it comes to crafting planets, chaos isn't an obstacle. It's just another tool in the workshop. Among the countless stellar graveyards drifting through space, one stands out like a work of celestial origami. The Butterfly Nebula, where a dying star has folded its final breaths into perfect symmetrical wings. This bipolar planetary nebula, officially named NGC 6302, isn't just beautiful, it's a violent masterpiece, a testament to the chaos and precision of stellar death. Captured in stunning detail by the Chandra X-ray Observatory, its wings stretch over 3 light-years across, glowing with the light of ionized gas heated to millions of degrees. What makes this cosmic butterfly so extraordinary isn't just its shape, it's the sheer force required to sculpt something so delicate from an explosion. At the nebula's heart lies a white dwarf, the smoldering core of what was once a star 5 times more massive than our Sun. As it shed its outer layers, this star didn't go quietly. Instead, it erupted in opposing jets, blasting material outward at speeds exceeding 600,000 miles per hour. But here's the mystery: those jets shouldn't have been so perfectly aligned. Stellar winds are typically chaotic, like a balloon deflating in random directions. The butterfly's flawless symmetry suggests something unseen was guiding the chaos. Perhaps a dense disk of dust and gas around the star, funneling its dying screams into two narrow beams. Imagine squeezing a water balloon at its equator. The water jets out the poles in orderly streams. That's the kind of cosmic physics at play here, only scaled up to stellar proportions. Chandra's X-ray vision reveals another twist. The wings aren't just hot, they're scorching. While the outer gas glows in visible light, the inner regions shimmer with X-rays, evidence of shock waves rippling through the nebula as fast-moving material slams into slower ejecta. These collisions heat the gas to temperatures rivaling the sun's corona, creating a shimmering, high-energy silhouette. But the real surprise lies at the wingtips, where X-rays fade abruptly. That sharp cutoff hints at an invisible boundary, maybe the edge of the original star's influence, where its ejected material finally meets and mingles with the interstellar medium. It's like watching smoke from a fire hit a glass ceiling, spreading out in a sudden, flat pancake. The most haunting detail: this butterfly is temporary. In 50,000 years, the nebula's delicate wings will dissipate into the void, leaving only the cooling white dwarf behind. But for now, it floats in space as a reminder of stellar mortality's strange artistry, a fleeting monument to the fact that even in death, stars can create symmetry from chaos. And perhaps that's the most profound lesson here. The universe doesn't just destroy, it sculpts, it balances, and sometimes, against all odds, it leaves behind beauty. Deep in the void between constellations Camelopardalis and Auriga drifts an enigma wrapped in cosmic silence. J0613+52, a galaxy that forgot to make stars. This shadowy expanse holds enough hydrogen gas to spawn billions of suns, yet its skies remain perfectly, unnaturally dark. No stellar nurseries ignite its clouds. No supernova paint its emptiness with heavy elements. Just an endless sea of pristine gas, swirling untouched for perhaps 13 billion years, as if the universe itself pressed pause on this pocket of creation. What makes the dark galaxy so unsettling is how it defies every expectation of galactic evolution. Most galaxies, even the faintest dwarfs, sport at least a few ancient stars, the smoldering embers of early cosmic fires. But J0613+52 appears frozen in its infancy, a celestial stillbirth where the spark of star formation never caught. Radio telescopes reveal its structure, a vast, rotating disk of gas nearly as wide as the Milky Way, held together by dark matter's invisible grip. Without stars to illuminate it, the galaxy was only discovered by accident, its hydrogen emissions picked up by the ultra-sensitive Green Bank telescope during a routine sky survey, like hearing a whisper in a soundproof room. Theories about its origins split into two camps. One suggests it's a cosmic relic, a rare survivor from the epoch before stars existed. In this scenario, its gas avoided the gravitational nudges that triggered collapse elsewhere, preserved by isolation or some quirk of its dark matter halo. The other camp argues it's a failed experiment, a galaxy that tried to form stars but lacked the necessary turbulence or metal content to cross the threshold. Without heavier elements to cool the gas, its hydrogen might have remained too hot and diffused to fragment into stellar seeds. Then there's the magnetism mystery. Recent observations reveal the dark galaxy's gas is magnetized, a property usually forged by stellar winds and supernova. But with no stars to generate such forces, where did these magnetic fields originate? One radical proposal: they're primordial, woven into the fabric of space during the Big Bang itself. If true, J0613 plus 52 could be a living snapshot of the universe's magnetic infancy, a fossil from a time when magnetism existed without stars to nurture it. The most haunting question isn't about its past, it's about its future. Floating in near total isolation, this galaxy may never collide with another, meaning its gas could drift unchanged until the end of time. Or perhaps some distant event, a gravitational ripple, a brush with dark matter will finally jolt it awake, igniting a firestorm of delayed starbirth. For now, it lingers as a cosmic paradox, a galaxy in form but not in function, a reminder that even the universe's most straightforward recipes sometimes yield surprises. In the grand tapestry of creation, the dark galaxy is an unfinished thread, one that forces us to wonder how many other silent shadows might be lurking, unseen, just beyond the light. Spinning through the cosmos like a celestial hula hoop, NGC 4632 defies every expectation of how galaxies should look. Most galaxies, even the majestic spirals, tend to keep their stars and gas neatly aligned in a single plane like plates spinning on a table. But this cosmic oddity breaks the mold with a dazzling polar ring, a perfect loop of gas and stars circling its poles at a right angle to the main galaxy disk. Picture a vinyl record with a glowing bracelet hovering perpendicularly around its edge, and you've got a rough idea of the spectacle. What makes this structure so rare isn't just its geometry, it's the sheer improbability of its existence. Polar ring galaxies account for less than 0.1% of all known galaxies, cosmic accidents requiring a precise and violent origin story. The leading theory, a brutal galactic hit and run billions of years ago. Imagine a smaller galaxy careening into NGC 4632's disk at just the right angle, its gas and stars ripped away by tidal forces and flung into a perpendicular orbit. Over eons, that stolen material would have settled into the orderly ring we see today, a fossilized testament to an ancient cosmic collision. But the real mystery lies in the ring's stability. Normally, such off-kilter structures would warp or dissipate over time, pulled out of shape by the main galaxy's gravity. Yet NGC 4632's ring remains crisp and coherent, its stars and hydrogen gas tracing a near-perfect circle. Recent radio telescope observations reveal why, a vast reservoir of dark matter acting as an invisible scaffold. This halo's gravitational influence likely stabilizes the ring, preventing it from collapsing back into the main disk or spiraling away into the void. It's a cosmic balancing act, one that suggests dark matter doesn't just anchor galaxies, it can also preserve their most fragile ornaments. Here's where it gets stranger. The ring isn't just a relic, it's a stellar nursery. Unlike the aging stars in the galaxy's main disk, the ring sparkles with young, blue hot stars, their formation likely triggered by the same collision that birthed the structure. Gas compressed during the impact would have ignited waves of star birth, turning the ring into a sort of circular assembly line for new suns. That makes NGC 4632 more than a curiosity. It's a laboratory for studying how galactic violence can seed creation. Yet the most tantalizing question remains unanswered. Where's the culprit? The smaller galaxy that supposedly donated this ring left no visible trace, no deformed core, no trailing stream of stars. Some astronomers speculate it might have been a gas-rich dwarf, its stars too sparse to leave a lasting signature. Others wonder if the collision was so catastrophic, the intruder was completely assimilated, its identity erased by time. Whatever the case, NGC 4632 stands as a monument to the universe's capacity for reinvention. A catastrophic encounter didn't just scar this galaxy, it adorned it, turning destruction into a crown of stars. The lesson, even in the vastness of space, accidents can become art. Every time we discover a galaxy like this, we're reminded that the cosmos doesn't follow blueprints. It improvises, leaving behind wonders that challenge our imagination and redefine what's possible. NGC 4632 isn't just a galactic oddity, it's proof that sometimes the universe's most breathtaking creations arise from chaos. Somewhere in the distant cosmos, a signal pulses with the precision of a metronome, a rapid-fire burst of radio waves so powerful it outshines entire galaxies for mere milliseconds. FRB 20190520b isn't just another fast radio burst, it's a prolific repeater, a cosmic Morse code operator that refuses to stay silent. Unlike the one-off blips that dominate FRB detections, this source has been firing off signals since its discovery in 2019, offering astronomers an unprecedented opportunity to decode one of space's most baffling phenomena. What makes this repeater extraordinary isn't just its persistence, it's the eerie structure of its emissions. Most FRBs erupt chaotically, but this one's bursts arrive in clusters, with quiet periods lasting roughly 16 days before the fireworks resume. That rhythmic pattern suggests something unseen is modulating its activity, perhaps an orbiting companion whose gravitational tug periodically blocks or channels the burst. The leading suspect, a highly magnetized neutron star locked in a slow dance with another massive object, may be a black hole or a dense, debris-filled cloud. Imagine a lighthouse whose beam is occasionally eclipsed by a passing ship, its light vanishing and reappearing on a predictable schedule. The plot thickens when you examine the bursts themselves. Some arrive with a distinctive downward frequency drift, a musical glissando where higher notes arrive slightly before lower ones. This tells us the signals are traveling through a dense, magnetized environment, likely the turbulent outskirts of the neutron star's magnetosphere. But here's the twist: the bursts also show signs of scattering, as if they've been threaded through a cosmic sieve. That implies an additional obstacle, perhaps a shroud of plasma left behind by a recent supernova or material stripped from a binary companion. Then there's the persistent radio glow. While most FRB sources go dark between bursts, this one emits a steady radio hum even when silent, a faint but unwavering beacon that hints at ongoing energy output. Some theorists suggest it might come from a pulsar wind nebula, a bubble of charged particles energized by the neutron star's rotation. Others propose the glow is evidence of an active accretion disk, with material spiraling onto the star's surface and generating continuous radio waves. Either way, this baseline signal offers a crucial clue. Whatever's powering the bursts isn't just an occasional flare, it's a relentless engine, the most tantalizing question. Why some bursts seem to follow patterns while others don't. One possibility involves starquakes, sudden fractures in the neutron star's crust that realign its magnetic field, releasing pent-up energy in predictable cycles. Another theory points to precession, the star wobbling on its axis like a spinning top, directing its beams toward us at regular intervals. Or perhaps the answer lies in the environment. If the neutron star orbits through a clumpy debris field, it might only produce bursts when plowing through dense pockets of material. Every time this cosmic repeater fires, it chips away at the mystery. Is it a lone magnetar throwing tantrums, part of a binary system we can't yet see? Or something even stranger? Fast radio bursts once seemed like random cosmic static, but thanks to persistent oddballs like FRB 20190520b, we're starting to hear the universe's rhythm beneath the noise. And with each new burst, the message gets clearer. Deep in the void, something is speaking. We just have to learn its language. Out in the constellation Cygnus, a gas giant named Kepler 1708b circles its star every 737 days, but the real mystery isn't the planet itself. It's the shadow trailing behind it. Scientists poring over Kepler Space Telescope data spotted something peculiar, a second, fainter dip in starlight following each planetary transit, as if something massive were riding the planet's gravitational wake. The best explanation: a moon. Not just any moon, a Neptune-sized behemoth dubbed Kepler 1708bi, a candidate so bizarre it would dwarf every moon in our solar system combined. If confirmed, it wouldn't just break records, it would shatter our understanding of how moons form and survive in alien star systems. The evidence hinges on three tantalizing clues. First, those secondary dimmings, small but consistent, appear like clockwork after each planet transit, suggesting an object locked in orbit. Second, the timing and depth of the dips imply a moon roughly 2.6 times Earth's radius, making it a mega-moon unlike anything we've seen. Third, and most compelling, the moon's inferred orbit aligns almost perfectly with the planet's equatorial plane, just as our moon aligns with Earth's rotation. That's exactly what astrophysicists would expect for a gravitationally bound companion. But here's the catch: detecting exomoons is like spotting a firefly hovering near a spotlight from 1,000 miles away. The signals are faint, easily drowned out by stellar activity or data noise. Some skeptics argue the dip could be a glitch, a hiccup in Kepler's instruments, or an unrelated starspot flicker. Others propose an even wilder idea. Perhaps the moon isn't a moon at all, but a second planet in a bizarre, resonant dance with the first. The challenges of confirmation reveal just how cutting-edge and borderline impossible exomoon hunting truly is. Unlike planets which block significant starlight during transits, moons cast shadows hundreds of times fainter. Add the fact that Kepler 1708b orbits a dim, distant star, and the signal becomes needle in a haystack subtle. Even the Hubble Space Telescope, our most powerful eye on the cosmos, struggles to validate the find. Researchers have turned to statistical tricks, running thousands of simulations to rule out false positives. The results promising but not definitive. The moon's existence currently hangs at 3 sigma, a 99.7% confidence level that sounds impressive until you remember particle physics demands 5 sigma for official discovery. What's truly mind-bending is how this moon, if real, could have formed in the first place. Moons this large shouldn't exist under conventional models. In our solar system, mega-moons are unheard of. Even Jupiter's Ganymede, the king of moons, is just 40% Earth's radius. One theory suggests a violent past. Maybe the moon started as a planet itself, captured during a chaotic early phase when the system was crowded with free-floating worlds. Alternatively, it might be the survivor of a cataclysmic collision, like our own moon, but scaled up to monstrous proportions. The planet's wide orbit offers another clue. Far from its star's gravitational grip, tidal forces would be weak, allowing such a massive moon to remain stable over billions of years. The debate rages on, but one thing's certain: Kepler 1708b has already changed the game. Whether it's confirmed or debunked, its mere possibility forces us to expand our cosmic imagination. Maybe giant moons are cosmic rarities, or maybe we've been looking in the wrong places, blind to the giants hiding in plain sight. Every flicker of data brings us closer to an answer, reminding us that the universe specializes in the extraordinary. After all, if a moon can grow to the size of Neptune, what other wonders are waiting beyond the edge of our telescope's reach? Saturn's largest moon, Titan, hides a secret beneath its thick orange haze, seas of liquid methane that dance to the quantum beat of the cosmos. While Earth's oceans ripple with familiar waves, Titan's hydrocarbon lakes produce eerily precise, millimeter-high ripples that behave more like particles in a physics experiment than liquid on a planetary surface. NASA Cassini spacecraft first spotted these uncanny patterns, revealing waves so small and orderly they defy conventional fluid dynamics. This isn't just alien weather, it's a glimpse into a world where quantum mechanics sculpts the tides. What makes Titan's waves so bizarre is their scale. On Earth, even the gentlest breeze creates chaotic capillary waves, tiny, short-lived ripples that quickly dissolve into disorder. But Titan's methane waves maintain near-perfect synchronization, as if choreographed by some unseen quantum conductor. The secret lies in the moon's surreal environment. With surface temperatures around -180 degrees Celsius, methane exists in a delicate balance between liquid and gas, its molecules moving sluggishly in the cold. That sluggishness reduces turbulence, allowing wave interactions to exhibit coherence, a property normally seen in superfluid helium or Bose-Einstein condensates, not planetary oceans. It's as though Titan's seas are caught between classical physics and the quantum realm, their behavior blurring the line between fluid dynamics and particle physics. Even stranger, these waves might be governed by surface tension rather than gravity. On Earth, gravity dominates wave formation, but Titan's low gravity and methane's unique properties elevate surface tension to the starring role. The result is waves that propagate like synchronized vibrations, their crests and troughs aligning with unnatural precision. Some researchers compare it to a drumhead vibrating in slow motion, where each ripple is a note in a cosmic symphony. This could explain why Cassini observed wave heights rarely exceeding 5 millimeters, even during Titan's windy seasons, a far cry from Earth's storm-driven swells. But the real quantum twist involves solitons' rare, self-reinforcing waves that travel without dispersing. On Earth, solitons appear as freak anomalies like the infamous tidal bore of the Amazon. On Titan, they might be the norm. Models suggest methane's low viscosity and Titan's calm winds could allow solitons to dominate, creating waves that maintain their shape indefinitely, like photons holding their quantum state. If true, these waves wouldn't just look quantum, they'd be quantum, their behavior echoing the wave-particle duality of subatomic particles. The implications stretch beyond celestial curiosity. Titan's seas could be a natural laboratory for studying quantum hydrodynamics, a field usually confined to supercooled labs on Earth. Imagine probing the origins of quantum coherence in an environment where nature has been running the experiment for billions of years. And there's a haunting possibility. If life exists in Titan's methane lakes, it might have evolved to harness these quantum waves, using them for communication or energy, a biology built not on water, but on the delicate interplay of fluid and quantum physics. Titan doesn't just challenge our understanding of moons, it redefines what a liquid world can be. In its methane tides, we see the universe playing with physics in ways we've only begun to decode. Every ripple is a whisper from the quantum void, a reminder that even the most familiar phenomena, waves on a shore, can become extraordinary under the right alien sky. When Oumuamua streaked past the Sun in 2017, it left behind more questions than answers, an interstellar visitor behaving unlike any comet or asteroid we'd ever seen. This tumbling, cigar-shaped object accelerated away from the Sun in ways gravity alone couldn't explain, sparking debates that still rage years later. The leading theory, outgassing comet like jets of vaporizing material nudging it off course. But here's the catch, no visible tail or coma was detected, something even the faintest comets can't hide. It's as if Oumuamua vented gas through hidden tunnels, leaving no trace of its propulsion. Then came the more provocative idea, could it be artificial? Harvard astronomer Avi Loeb famously suggested Oumuamua might be a light sail, a thin, reflective structure propelled by stellar radiation. Its unusual brightness variations and trajectory do loosely fit the profile of a discarded solar sail drifting between stars. While most scientists remain skeptical, the hypothesis forced a broader conversation. How do we distinguish natural oddities from potential extraterrestrial technology? The truth is, we lack a universal rulebook. Oumuamua's refusal to fit neatly into existing categories exposed a gap in our understanding of interstellar objects, prompting astronomers to design new classification systems for future visitors. Recent studies have added layers to the mystery. Simulations now show Oumuamua's acceleration could stem from hydrogen ice sublimating beneath its surface, a process invisible to telescopes but potent enough to explain its movement. As a primordial object forged in the frigid outskirts of an unknown star system, It might have carried pockets of molecular hydrogen that vaporized in sunlight, acting like a stealthy thruster. Others propose it's a shard of a Pluto-like exoplanet, broken apart by a collision and hurled into the void, its nitrogen-rich composition accounting for the odd reflectivity. The most tantalizing development, Oumuamua might not be alone. The discovery of 2019 Borisov, a more comet-like interstellar visitor, proved our solar system is a crossroads for cosmic drifters. Upcoming telescopes like the Vera Rubin Observatory could spot dozens more this decade, offering fresh clues. Each new visitor is a time capsule from distant star systems, and Oumuamua, the first, remains the benchmark for strangeness. Was it an exotic ice fragment, a rogue planetary fragment, or something even more unexpected? Until we catch another, its secrets linger, a reminder that the universe is far more inventive than our textbooks. What's undeniable is how this interloper reshaped astronomy. It forced us to rethink the diversity of objects sailing between stars and humbled us with the realization: sometimes the most profound discoveries don't announce themselves with fireworks. They whisper, leaving us to piece together their stories long after they've vanished into the dark. From singing comets to diamond rain, rogue black holes to cosmic question marks, the universe has unveiled its strangest secrets in this journey through 30 space oddities. Each discovery shatters expectations, like the dark matter hurricane barreling through our galaxy unseen, or the zombie star T Ursae Minoris that refuses to die, erupting again and again against all stellar logic. These aren't just curiosities, they're cosmic challenges, forcing us to rewrite textbooks and rethink fundamental laws. The Tasmanian Devil Pulsar's machine gun bursts defy physics, while the cannibal galaxies' feasts reveal how violence builds the cosmos. Even familiar sights like Betelgeuse's great dimming proved we've barely scratched the surface of stellar behavior. What ties these oddities together is their audacity. They exist where they shouldn't, behave in ways they can't, and linger just long enough to upend our assumptions. The dark flows tug toward the unknown, hints at realms beyond our horizon, while the intergalactic superhighway's invisible threads weave galaxies into a web we're only beginning to map. Even seemingly simple waves on Titan's methane seas whisper quantum secrets, proving that the universe delights in blurring the lines between the mundane and the miraculous. The beauty of these mysteries isn't just in their strangeness, it's in the doors they open. Every oddity is a clue, a breadcrumb leading toward deeper truths. Could rogue black holes rewrite our understanding of galactic evolution? Might the Space Jellyfish Nebula's eerie pulse reveal new states of matter? With telescopes like JWST and the upcoming Rubin Observatory, we're on the brink of uncovering even more wonders. So now it's your turn. Which of these cosmic rebels captured your imagination? The diamond-shrouded hellscape of WASP-121b, the rhythmic radio cries of FRB 20190520b. Or perhaps the haunting silence of the dark galaxy, a place where starlight never dawned. Drop your favorites in the comments and stay curious, because in a universe this inventive, the next great discovery might be lurking just beyond the edge of our sight, waiting to astonish us all over again.